in progress. So sampling distributions tend to be relatively normal. And I'm using normal in a very special context here that I'll explain more in a minute. Tend to be relatively normal for a large enough sample size. Next, what does normal mean? A normal distribution is a symmetric bell-shaped distribution where about 67% of values fall within one standard deviation of the mean. 95% of values fall within two standard deviations of the mean. And about 99.7% of values fall within three standard deviations of the mean. And this collection of percentages related to standard deviations is called the empirical rule in statistics. And the only thing that has to be true about the samples is they have to be big enough. Usually big enough is like more than 20. That tends to be big enough. There's some special things about proportions based on the number true and the number not true, depending on what we're looking at. We'll talk about that later, but this is the general rule. And it doesn't matter whether we're talking about proportions or means, as long as the sample size is large enough, we're going to have distributions that fit this pattern. Okay. Even if and remember, distribution is just a histogram. Even if the histograms of the samples don't have a normal bell-shaped curve, then this is going to be true as long as the sample size is big enough. Okay. Important things, other reminders. What is a sampling distribution? It means lots of things, but for us, examples of sampling distributions are distributions of sample means. All right, we take lots and lots of samples, all of size 74. And all we do is report the mean of each of those samples. Okay, so we get 1,000 people to go out, randomly find 1,000, say, adult females, get their BMI, and only report the average of those 74. So then I have 1,000 averages, and if I graph those 1,000 averages, it's going to look like a symmetric bell-shaped curve, because 74 is a big enough sample size. And it's also true for proportions. So 2 those are the main ones we're focusing on in this course. And again, what's a distribution? It's just a histogram of a bunch of numbers we calculate. So this is for histograms of means, not individual values, means, or histograms of proportions, percent of a group where something happened. Not individuals. This is not about individuals. It's about samples, repeated sampling. And we have technology that can easily do repeated samplings like shuffling lots of decks of cards, is what we're planning on to do. Which is kind of a weird abstract concept, but it's super important to statistical predictions. Right. So, other things about a normal distribution. So, defining normal distributions. We need two pieces of information. We need the mean of the distribution. And we need the standard deviation of the distribution. These are sampling distributions, which is lots and lots of samples. And the other name for the standard deviation of a sampling distribution is standard error. Which we've looked at a little tiny bit in Stacky. The Brooks mentioned it a few times. And just to clarify, these are sampling distributions. Which means we have lots and lots and lots of samples to play with. And that's called the standard error. So a normal distribution is a mathematical equation. If you took a class like pre-calculus, you've seen this kind of equation. It's related to a magic number called E, which is about 2.7-ish. I don't really care about the equation. I just need a calculator that can draw a normal distribution. So what I'd like you to head over to is go to the StatKey homepage. I'm going to leave this one here for a moment. And on the StatKey homepage, further down, there's the second to last line says theoretical distributions, and one of them is called normal. The one that's graphed here in StatKey is called the standard normal distribution. I want to mention a couple things about this before we mess with it. Let's see all of that. So this particular one is called the standard normal. You could also consider it a distribution of z-scores. We're going to review what a z-score is today. And the standard normal, the mean is 0, and the standard deviation is 1. That's what makes it the standard normal. 0 is in the middle, standard deviation is exactly 1. So I want to compare that to the distribution, sampling distribution that Stacky has for body temp. Back here, I was in the StatKey randomization test for a mean. I'm just going to reload this page for fun. And the body temperature data is here where there are 50, I believe these were college students. They had an average body temperature of 98.26. We usually believe human body temperature internal is about 98.6. This is different, right? So I have a hypothesis, a null hypothesis value. I have a sample. I can generate thousands of samples. And that's a relatively symmetric bell-shaped curve. It should be a normal distribution, roughly. Okay, what's the center of this distribution? 98.6. Okay, what's the standard deviation of this distribution? Well, that would be up here, the standard error. So I need a screenshot of this. Wrong button. I want that button. Let's get all that. To new page, please. Okay. So this graph here is a normal distribution. And it's a distribution for means of sample size 50. Or again, their means, what kind of a mean? Average body temperature. What's the mean of this distribution? Well, the center down there is 98.6. This has a mean of about 98.6. And the standard deviation here, this is important. It's not the standard deviation of the sample. It's what Stackey calculates to be the standard error for this set of 7,000 samples of size 50, and it is 0.108. So that would be the standard error, and the standard error here is 0.108. And the shortcut for saying you have a normal distribution with this mean and that standard deviation is to write a capital N and then state what the mean is, comma, state what the standard is. So this is normal, mean 98.6, standard deviation 0.108. And I can use the Stackey normal distribution graph to come up with a p-value for this situation. So that's what I want to try and do next. So I'm going to do it in two different ways. I'm going to find the p-value using the randomization test here. Then I'm going to find the p-value on the normal distribution. And that's the new thing we have to get used to this week. So we're doing the same thing we did before. We're just adding a new way to gather evidence that something is significant or not. So back here, so I'm going to go with a left tail test because the sample has a lower average than what we think is average human body temperature. So I'm going to go left tail, and then I'm going to type in the 98.26 from the sample. And Stackey says, for this particular randomization, we get a p-value of 0.00057, which is pretty small, which means I have evidence that average body temperature of college statistics students is lower than 98.6. So that would be my alternative hypothesis. Can I state it's human body temperature of statistics college students is 98.26? No, I need a confidence interval for that. I haven't done that yet. And now comparing this to the normal distribution calculator. To use the normal distribution calculator, you need to type in the mean of your distribution and the standard deviation. So here I would go to edit parameters. My mean is 98.6, and the standard deviation is the standard error from that graph, which is 0.108. Right, the two numbers I identified before from the distribution. And once I have those in there, I can do a left tail test, and then I just type in the sample value down here. So the sample value is 98.26. And I should get a similar p-value. Will I get the same p-value? No. This is a theoretical calculation based on what I believe the mean of the distribution is and what I believe the standard error is, which I used a computer to approximate based on the sample distribution. But this is a different way to calculate. How is this one calculated? It's kind of complicated, but brief note on that. Let's look for normal distribution equation. That's the equation for a normal distribution. So Stackey does some calculation based on that right there. I don't care about the details. If you take like a second or third course on statistics, you might get into the theoretical details of that equation. We have this beautiful graphical calculator that just deals with it for us there. It's nice. Note, if we rerun this randomization here, so reset, generate thousands of samples, I should get about the same standard error, 0.108. Sometimes it'll be a little tiny bit different. The middle is still 98.6 because that's what I set the null hypothesis to. And if I do the left tail test and enter the sample statistic, 98.26, I get a similarly small p-value. Okay, so are the p-values I got in the same ballpark? Well, I did two randomization p-values. The first one was 0.00057. This one's 0.00043, and the theoretical version is 0.00082. They're in the same ballpark, right? They're around the same power of 10. They all indicate reject the null hypothesis. The evidence supports your alternative hypothesis that average body temperature is lower than 98.6. Okay, so this is the new twist that we're adding. So there's a bunch of homework assignments where I just ask you to use the Stackey theoretical normal to make some calculations to get used to it. You just plug in the mean and the standard deviation. Yeah. Alternative that I want to talk about, because here I mention that a standard normal is also a distribution of z-scores. So I just want to go back and remind you all way back from chapter week 2. We're on week 7 now. What was a z-score again? Does anybody remember?
It's like a portion of the part of the graph.
Yeah, it's related to a histogram. It's related to another special calculation.
Related to the standard deviation.
It's related to standard deviation. Yeah, all a z-score does is count how many standard deviations you are from the mean. That's all a z-score is. So z-score is a count of the number of standard deviations some value is from the mean. Okay, so for example, with what I was just playing with, we had a population mean mu of 98.6. We had a standard error, which is a standard deviation of about 0.108. And we had another value from the sample, x bar, which was 98.26. So to find the z-score there, I would just see first how far apart are the two means. So I would take the 98.26 from the sample, subtract the 98.6 from the null hypothesis. So that tells me how far apart they are. And then I just say, okay, how many of these fit in there? So then divide by the standard deviation. And that'll count how many standard deviations apart they are. Let's whip that calculation out. Whip out a calculator, please. What is the z-score for this sample? All right, so let's just type it in. So you need parentheses on some calculators. 98.26 minus 98.6, close parentheses, divide by 0.108. And this says that the z-score is around -3-ish. Okay, so I'm going to call it, let's grab 3 decimal places, -3.148. Anyone else get that? Okay, good. Just making sure I didn't screw this up. So -3.148. So I'm getting a z-score here of about -3.148. So my sample is more than 3 standard deviations to the left of what I believe the center is. Remember our 95% rule? Most data should be within like 95% of most, 95% of data is within 2 standard deviations. I'm way outside of that. Is this an unusually low value compared to what we expected? Yeah. And that's what the p-value told us too. So it turns out another way to see if something is unusual is to look at the z-score. If the z-score is way out there, it's like, whoa, that's different than I expected. It's not close to what I thought the center was. Right. So this is an unusual z-score. . So what this is, in this case, it's further evidence that I should reject the null hypothesis. I have a z-score that's way out on the edge and I have a small p-value. Two pieces of evidence that say reject the null, your data supports the alternative. And that's what chapter 5 is about, to say that all of these sampling distributions are relatively normal. So we could, in addition to running the simulation, we could just use a theoretical normal distribution as long as we know a mean and a standard deviation. If we don't have those two, then we can't use the theoretical one, we can only do a randomization. But we can use the randomization to double check with the theoretical. And they'll usually be in line. Will they have exactly the same p-values? No, not exactly. So what is a normal distribution again? Anyone? That's it. Okay, yeah, perfect. And what is a standard normal distribution?
The distribution of these.
Yeah, which means the mean has to be 0 and the standard deviation has to be 1. Let's plug in this z-score to the standard normal and see what we get. So here, theoretical normal, I'm going to just reset the plot. And now I have a mean 0 and a standard deviation of 1. So now it's set up for me to plug in a z-score. Okay, I was doing a left tail test, so I choose left tail. And then I just plug in the z-score I calculated. Mine was negative 3 point, I think it was 148. And what's my p-value? 0.00082. Same as I got before when I had the mean of 98.6 and the standard error of 0.108. So it turns out there's a couple ways to make these kinds of calculations happen. We have choices. In general, what I'm going to do whenever possible, and I have to do a hypothesis test, I'm going to do a randomization one, and then I'm going to check with the standard normal and see if they match. If they're close, then I say, okay, I think I have things set up right. And then I can either reject or fail to reject based on that. All right, we should take a little break. That was intense. All right, stand up, stretch, grab a snack.